Hello. This video will be talking about maximum and minimum values. No? So this will be a very short explanation to what it is. So if you want a thorough explanation, you could just read the whole content, no? Given with the PDF, no, you could just run through the contents of this. But however, the whole presentation will be just the glimpse, no, a short explanation to how what is the maximum and the minimum values, how could we use this information or these terms, no, because these are um this is one of the parts of the the curves. This is one of this is partly, yeah, this is part of the curves. Now when we derive the curve, we have what we called as the maximum and the minimum values. So let's just proceed. So so by definition, let's just read this one. So let C be a number in the domain, capital D, of a function f. Then the f of C, so the C is any number which is part of the domain, is the one absolute maximum value of the function on domain. So if the value of, let's say, the C is distributed to the function, the value of it is greater than or equal to the function, no, of all sets of values of the domains, no. So it just mean that it is the highest, or the, is, if we say the x and the y, we have the highest value of your y, no, yeah, all throughout the function. And number two would be the absolute minimum. So this time, since it is minimum, so if if the C, let's say the number, the specific number that we distributed to the function is the lowest value that we could get out from all of the values of f of x. So there is a figure that you can see below. It has dots, no, there are two dots. And just to present, just to elaborate what is the absolute maximum and the absolute minimum. So this one is what we call the maximum value, or the absolute maximum. And what we have here in the lower part would be the absolute minimum, no? So in simpler term, we could call it the maxima for the absolute maximum, and minima for the absolute minimum. But yeah, by English, no, maxima means a plural term for maximum, also with the minimum. Okay, so okay, so I'm just skipping the other terms that being elaborated by the book, no. But what we have here in figure 2 is that we have absolute minimum for the function of a, and absolute maximum for the function of d. So we have local minimum for the function of c. um we have another local minimum for the function of e, and we have local maximum for the function of b and f of d. So we have the definition that the number of the function of c, or the any number, is a local maximum if the value of the function, if it is the most lowest, or it is the least value that we could get out from the any value that we could distribute for the function, which is near of the value c. And for, I don't know, what I mean is the highest, the maximum value, because it's the maximum. So it is the greatest value that we could get if we distribute, no, any values of the function. So let's just say that when we distribute the c, it is the highest or the maximum the value that we could get. For local minimum is we have the least value, no? So what is being meant by that? Let's say that we have an interval from A to C. So I'm just taking note of this. So from A to C, let's say we just consider this part, no, from A to C. We have here a maximum value of f of b, right? So we have maximum value, no? But however, we know that since we are just closing the interval of between this part of the curve, we know that there is much more greater than that, which is f of d. And so the correct term for this one would be local maximum, because it is the highest value from the given interval, but it's not totally the maximum value. We're just considering it as the maximum value because we are limited to the given interval, no? And we have here the um yeah, we have here the f of a, which is, as we could see all throughout the graph, it is the absolute minimum, no? But given with the interval a to c, we could say that it is the local minimum, and also it could be the absolute minimum. So your f of a has two um two names, no? It could be the local minimum, and it could be the absolute minimum, because as what you could observe with the graph, no, since we are considering only for the intervals from a to c, it is the minimum, no, or the local minimum. And if you look, you are expanding the curve, it is the lowest value that we could get, no? And so if we expand this, no, yeah. And so if we change the interval, no? Let's say, let's change this interval. Okay. Let's say from C to E, and we will not refer again with A to C, we just focus on the C to E. And what we could see is that it has a maximum value at f of d, this one. And also if we observe it, no, we widen the observation, it is the absolute maximum, and it also the local maximum from C to E, no? So yeah, and referring to its minimum, or the minimum value, we have E, no, the f of E, in which this is the local minimum, but we know if we expand the curve, it is not the absolute minimum, because the absolute minimum is the f of a, as what we could observe in the graph. So yeah, if you are not sure, no, let's say you are just giving this in this interval, no, and you just considering the graph from the given interval, and you don't want to expand, you could just say it's the local maximum and minimum to be safe, no? However, if you really want to really find the absolute and maximum, then you need to really expand your observation to find the real absolute minimum and maximum values. So more explanation, no? In figure 3, we have here at interval I, no, from the values that we observe from the blue region at 4. It is the local minimum at the value of 4, no, when we distribute the value of 4 to the function. And proceeding with the value of 8, it is the local maximum. And yeah, with expansion of the curve, we know that when the function is approaching to 0, I don't know what happens, but as you can see here, what you can see here, it is increasing, no, but we do not know what happens here. We just assume that it is still increasing, so we could not say that it is the absolute maximum. Okay, going forward to the value of 12, or the interval of k, what we could see here, it is the local minimum, and it is also the absolute minimum, no, since the regions, the n regions is increasing, and so we could say that there is no minimum values of the curve that we could get. And so this part, the right side is increasing, no, the left side is increasing, the right side increasing, so we could say that at 12, no, at f of 12, you could get your absolute minimum, no? So which is at 12. So these are just terms, no. Don't be hesitate, no. These are just terms that we could use, no, in terms of how do we define these values, which is part of your curve, no. So just like what I've said, maximum and minimum values are just terminologies created in which these are special values that we could observe, no, when we apply these kind of things into the real problem. So sooner we could apply this one, but yeah, let's go to the terminologies before we get into the problem, no? So these are the things that we should understand first, no. Okay, so how about if we could use an example, no, for the maximum and the minimum values. So let me just find the example of the book, no. So okay, let me just transfer this to a note. Okay, okay, this one. So we have here an equation. The equation is a trigonometric function, so that is cosine of x. And what we know with the function cosine, it's when we graph this, it is a wave, no. Partly it is a repetitively curve, no, with y to x coordinate plane, and we have x as your values are in radians, no. So what we could see here is we have multiple values of your maximum, absolute maximum, or your maxima, and you have um multiple values of your minima. So you know that, yeah, these are your maxima, this one, right, this one also, because it's just although these values are just the same, but it is a trigonometric function, and it's so just repeating of your graph, no. So those are the things that we consider for trigonometric function. There's no problem in here because your values are fixed, no. When we use that value, we just use one value because it's just one, no? Dili man na siya naglahi-lahi value, and so there's no problem with this one. Although what we know that since it's a trigonometric functions, you have you have repetitions, no, of your maxima and your minima. So here, what we know here it is at f of 0, and what we know here it is at f of 2 pi. So yeah, so you have multiple values of x that could be your maxima, and multiple values of your x also that could be your minima. Ay, yeah, minima. Okay. Um, yeah. So what we could do here with this kind of situation is that we could say that uh when your cosine of x is equals to 1, it is your ano it is your maximum, right? So sorry, cosine of x when equals to 1, it is your maximum. Let's say this is 1, no? All throughout this one, this is 1. And so we could say that at cosine n pi x, it is equals to 1, no? Let's just put it pi x, no? Or, uh, I'm sorry. So, or, just erase this one. So that is cosine 2n pi. So when n is equals to 0, this becomes 0. No? When n is equals to 1, this becomes 2 pi. So at 0, so at 1, no? At n is equals to 0, at n is equals to 1. So that is 2 pi. And if n is equals to 2, this is your 4 pi, no? Which is still equals to 1. So that are series of values of your maxima, no? And same goes with your minima, no? So I think this is just cosine n pi. So yeah. So at ano no. Or yeah. So for your maximum values is said here. So that is cosine of 2n plus 1 times pi, no? Which is equivalent to -1. So when n is equals to 0 here, so that becomes cosine pi. So this one, n is equals to 0. This becomes -1. And if it's one, that is cosine of what? Yeah, 3 pi, right? So that is still equivalent to -1. So these are just series of values of your maxima and minima, no? So let's go okay, let's go forward with another equation. Let's just say if we have a parabolic function, let's say it's x squared, and we know that in the graph of f of x squared, this is it opens upward, no? So this is f of x equals to x squared. And what we could get in this graph is we have minimum values. So if we derive this one, so that is f of x equals to 2x, no? But however, our minimum values is this one, no? So at f of 0, this becomes 0. And since this is parabolic, it opens upward, so it continuously becomes greater, no, as we put greater values of your domain. So it means that your minimum value is 0, but we don't have maximum value because it continuously becomes greater as we go along to greater values of your domain. Okay. So what if okay, what if we have a cubic function? Let's just say it is f of x equals to x cubed, no? And if we graph this one, you know that the graph of a cubic function is more like this, like that. So yeah, what we could say in this graph is it continuously becomes larger as as your domain becomes larger also, or increasing, and it also becomes lesser as you go to the negative x-axis, no? So it means that you don't have minimum values and no maximum values as your observation of the graph, no? Because it's just continuously becomes lesser and it continuously becomes greater. Okay. Okay, so okay, let's proceed now. Let's have a clear equation now. From the given of the book, we have here, okay, f of x, which is equals to 3x to the power of 4. Let me just change the color. So that is f of x, which is equivalent to 3x to the power of 4. And minus 16x cubed plus 18x squared with an interval of -1 as your x is greater than or less than to 1 and less than or equal to 4. Okay. So yeah, so we could graph this one, no? Um which just draw its graph. Or let me just copy the graph of the book, no? So we could uh, yeah. Okay, so this is the graph of 3x to the power of 4 minus 16x cubed plus 18x squared. And we have an given interval of -1 to 4. Ano? So, photo lang po dira. And as you can see with the graph, so since this is a degree of 4, so you have at least kaduha na ano, the curve, the curve is fluctuating, no? And what you can see is that we have we have, with the given interval, we have a max, minimum, no? Or let's just say mm, maximum also, no? Okay. So uh so at f of 0, what we know that, as we can see in the graph, no, at f of 0, it is equals to 0, no? And also at f of 3, this is equivalent to -27. um this both value is we could consider as the local mix minimum, no? We could say from interval from -1 to 2, we have a local minimum of 0, and from 2 to 4, we have local minimum of negative. Yeah, um, we have a local minimum of 3, which give us -27. However, for your domain 3, or x is equals to 3, we have here the absolute minimum value, no? Because it's the lowest value that we can get all throughout with the graph, all throughout with the curve, no? So yeah. And for local maximum, okay, let's just say that between the fluctuation of the curves at f of 1, you could say that it is a local maximum, no? But however, with the given interval that we could see, since this is a closed interval, it does not continues with the given interval. So it means that we are just limited with the graph that we could see, no, in the figure. So as we cut through the value at -1, we could see that it is the highest value we could get from the given interval. And so, given with this interval and with this curve, what is your absolute maximum? No, is it is at -1, which is we could get the value of 37. Okay? Yeah, but your at x equals 1, it is the local maximum, as you can see in the graph. So these are very situational, no? Because there are times that you are not given with intervals, so this is continuous function, and there are just functions that are just given with intervals, and so you are just considering with intervals and also with the maximum and minimum values. Okay, so what we could see here, you could use four computations, no? The end parts, we should consider that because it could be the maximum or the minimum values, no? And also with the maximum and minimum values that we could get from the intervals, no? From the inside or from the values between those intervals. Okay. So let's just proceed with the PowerPoint. Okay. So we have here mga theorems, no, for maximum and minimum values. These are theorems, so let's just say that we have proofs, but it's not totally given as law. But however, we could use this and we could not use this, no, because it's a theorem. So if the function is a continuous, let's say it is a continuous, and you are you're given a close interval, let's say from a to b. Okay, so the function obtains an absolute maximum value at f of c and absolute minimum value at f of t. Okay, at some numbers at c and d in the given intervals of a of b. So as what we could see from the previous example, no, kay situational kaayo, you have you just need to understand, no, the definitions of the maximum, the minimum values, and say we have absolute and we have local now. But it is very tricky when you are given with a close interval. So from the figure below, we have three situations, no. Your first graph is that your intervals are not the maximum and the minimum values, the absolute maximum and the minimum values, because we could really see that the values of the C and D are given with the lowest. It also is the local maximum and minimum, and it also is the absolute, no? From the middle figure, you have one maximum, absolute maximum, okay? And you have one minimum, absolute minimum, which is part of the interval value. So your B, no, on the middle figure is your absolute minimum, no, because you are just observing with the given interval and you're not continuing, no, you are not expanding the graph here. So at the third graph, we have here two absolute maximum values, because of the given curve has so many, yeah, so many curves, no? And you have two values of your absolute maximum. And I just say that, yeah, C1 and C2 are equal values of Y. And so you have two values of your maximum. And you have one value of your absolute minimum. So that's just it. So what you just need to know is what are the definition of these terms, and just by looking at the graph, you could say that these are the values, no? So, para dili lang jud malibog, you just understand the definition because it could be unique in some parts, no? So, more explanation to this. So, at figure 9, so this function has minimum value, no? So, at f of 2, it becomes 0 and it becomes the minimum value. But as you can see, this is not continuous, no? Ning putol siya at your x is equals to 1, no? So it means that we could not really describe what happens between there. So there is no maximum value. Continuing with another figure, we have figure 10. So this one, since it is hollow at the given point at f is equals to 0, and no, at f of 0, it is unknown, no? So, and also in the right part, at it goes near to x is equals to 2, it becomes larger and larger and it is continuous. So what we could conclude is we don't have no maximum and minimum. It's just that. Okay, so let's proceed to Fermat's theorem. So, yeah, this Fermat's theorem might be useful, no, in terms of applications. So this time, this kind of this kind of this kind of terminology could be applied with also the derivations, no? So by definition, Fermat's theorem is if the function has a local maximum or minimum at, let's say, C. So again, so if the function has local maximum or minimum, and if the derived function, no, with the same value of your maximum and the minimum value exists, then we could say that the derived function of C is equals to 0. So those are this is the value of the C. So we could say that you could derive this one and you just equate it to 0 to find the value of your C. So by reverse engineering, reverse solution. Okay. Because it happens that you are trying to find the value of C. By using Fermat's theorem, you will apply like this. Okay. And as a continuation with that theorem, no, we have what we call a critical number, no, and critical number is the value of the C. So when we derive the function and equate to 0, and we go along with continuing to finding the x, no, when we equate the derived function which is equals to 0, we are trying to find the critical number, no, when x is blah blah blah, when the derived function is equals to 0. Okay, so it may or may have a value, but we just need to understand also that some parts of the function, let's just say it has no maximum and minimum value, we could still derive this and we could still equate to 0, no, we could apply Fermat's theorem, no, but yeah, you could say that it is the critical number, no, based on the solution. But giving back to the definition, there is no maximum and minimum values. Okay, proceeding. So if the function has a local or minimum, local maximum or minimum at the given c, at the given critical number, then yeah, c is the critical number. And it's so if there is no local or maximum, then yeah, maybe that c is not a critical number of the function. Now, if the function is continuous, there's no problem, no? But there are some factors that we may encounter a given function with a given interval, just like what we solved earlier. So we have what we call the closed interval method. So to find the absolute maximum and minimum values of a continuous function, okay, on a closed interval. So let us first find the values of the critical numbers of f in the given interval and find the values of the function of the interval. So you need to find the critical number first, no? Then substitute or plug in those values in the function. And again, since you have intervals, two values of intervals, so you still need to plug in those values in the functions and compare the results, no, that is the number 3, compare the results, so which one is much lesser and which one is much greater. So if the value is much lesser with the given interval, so your absolute maximum is in between is in the interval. So if it's not, it is on the critical numbers. So again, I'm still trying to describe this, but yeah, it is still much be greater to explain this with a given problem, no, solution. So we will try to solve, no. We will apply this one. So let's just transfer to yeah, this writing board, no. Okay. Again, no, this explanation is a short explanation, no. I still encourage you to dig down on the definitions. There are much more written explanation in the book, no. So this video is a shortcut, no. So it may understand, but it's better if you read the whole thing. Okay, so we have a given function here. So f of x is equal to x raised to 3/5 power times the quantity of 4 minus x. Okay. Let's say we derive this. The problem being asked is find the critical number, no? So find the critical number. So from the definitions that we get, no, let's derive this. So f prime of x, this becomes, yeah, we will use product rule. So this is x to the 3/5 times negative 1 plus 4 minus x times 3/5 of x raised to the 3/5 minus 1. Or you could say that minus 5 over 5. So you could easily yeah, extract the fraction. So this becomes negative x to the 3/5. This becomes 4 minus x parentheses of 3/5. This becomes x to negative 2/5. Right? No? So going along with the equation, this is, yeah, so this becomes 12 over 5x to the negative 2/5. This becomes negative of 3/5. So this becomes 5 over 5, no? So we will add the fraction. This becomes 3/5. Not mistaken. So yeah. So you could add the same, yeah, we could add the same exponent. So this becomes 5 over 5, no? Kanidere. So we could add it. So this becomes negative 8 over 5 x to the 3/5 plus 12 over 5 times x to the power of negative 2/5. Yeah. So yeah. So if we try to paano. So this is, yeah, this is negative 8 and this is 5. So this could be x cube and this could be x 1/5, right? Sakto ba? No, no, no. So this is, yeah, this is still 3/5. Let's just give it one fraction. So this is negative 8x 3/5 plus 12x negative 2/5. No? So you could say this is fifth root of x cubed, and this is uh we have, we should say this is 5. This is still 5, but this is fifth root of x squared. No? So this is, as we go along with the equation, this is equivalent to 5. Then, or let's tuloy ni ibalik, no? Kaya magninggubot man. So this is x2 fifth. So this is x3 fifth. So if we combine this, so this is x2 fifth. This is equivalent to negative 8x3 fifth times x2 fifth, right? Plus 12. So this is equals to 5x2 fifth, adding the exponent. So this is negative 8. So 3 plus 2 becomes 5. So this is negative 8x plus 12. Okay. So yeah, I think that's it. So what we know, if we find the critical numbers, we just equate this to 0, no, and find x. So if we cross multiply this function, so the denominator become cancel out. So what remains here is negative 8x plus 12 is equals to 0. And we could say that your x here would be 12 over 8, no? So it is, if we divide 4, no, this becomes 3 all over 2. So that is your critical number. So your C. C1 is 3 halves, no? So, or at x of 3, 2, that becomes your critical numbers. But if we, and so if, and what we know is that if we derive of f of x, no, it does not exist when we plug in the value of 0, no? This is your f prime of x, no, kanisha. And if we plug in the value of 0 here, say f prime of 0, if we plug in, no, the denominator with 0, this becomes math error. So let's just conclude that your second critical number is 0 because of that situation. Okay. Okay, so let's just proceed with another problem. So this one, we have given function of x cubed minus 3x squared plus 1. We have a given interval of -1/2. Yeah, your interval is x is greater than or equal to -1/2 and is lesser than or equal to 4. Now again, the first problem that we get is we just receive, or we are just given with an equation, no? And so there is no given interval. And the second problem that we have is we have a function here, but we have a given interval. By a closed interval method, we need to derive this one and equate to 0 and find the values of the critical numbers. Let's say, we have two intervals, no? Because if we derive this becomes x squared. And so there are two roots that we could get, no? And since it is a closed interval, we need to plug in the values of the interval and the values of the critical numbers. Okay, so if we derive this one, so this is, let's just say the requirement of this problem is to find the absolute maximum and the minimum values of the function. So we need to derive this one. So this becomes 3x squared minus 6x, no? So if we equate this to 0, so this is 3x squared minus 6x is equals to 0. So this becomes 3x times x minus 2, which is equals to 0. So you have two values here, which is x at 0 and x is equals to 2. Not wrong, no? So yeah, x is equals to 0 and x equals to 2. So we plug in the values of the critical numbers to the given function, no? Let's just say first at the first value, which is at 0, this becomes 1, right? So 0 cubed minus 3 times 0 squared plus 1, so that is 1. So at f of 2, this becomes 2 cubed minus 3 times 2 squared plus 1. So that is f of 2, which is equivalent to negative, yeah, this is 8 minus 4, 12 plus 1. So this is negative 4 plus 3. And then, since we already plug in the values of the critical numbers, we need to plug in the values of the intervals. So that is -1/2. So at -1/2, so that is -1/2 cubed minus 3 times -1/2 squared plus 1. So this is equivalent to F4. Yeah. And at F4, this is equivalent to, I don't know, at f of negative 1/2, this is equivalent to 180. Sorry. At f raised to the power of 4, that is equivalent to 17. Okay. So what we are trying to find here is the absolute, okay, absolute maximum and absolute minimum. Okay. So in the graph, as we could see, so before we conclude, no, in the graph, as we could see, let's say this is the graph. Okay. Finding the critical numbers would say, sorry, okay, mao daw ni ang function, graphs of function. Okay, finding the critical numbers would say that this is the end part of the given fluctuation, no? So, kuning naa diri mo ni imong mga critical numbers. But since you are given with the intervals, no, you are just given with the limited values, no. So let's say kani at number 4, tuning erase diri ha. So that is not continuous to the left side, so that is 4, and this is negative 1/2 here. So your critical numbers, as what you solve here, this is equivalent to 0 and 2, diba? So this is 0, this part here is 2, and say when we substitute the values of our critical numbers, at 0 this is 1, so this is 0 1, and at 2 this is negative 3, so that is 2 and negative 3 here. And when we distribute the values of your intervals, so at negative 1, this is at 1/8, so this is negative 1/2 and 1/8. At 4, this is 4 and 17. So since, and we know already the definitions of the absolute maximum and absolute minimum, yeah, by observation, your absolute maximum is the value of 4, and the absolute minimum would be at, since the interval is, since the critical numbers is much more lesser, so we conclude that the critical number of 2 is our absolute minimum. So supposedly, if this is continuous, our absolute maximum would be at 0. But since we are just limited with the interval, so it changes, no? It changes a lot because there is an interval given. Okay? So, ay lang kalibog, no? Okay, let's proceed to the last example now. And I will be just attaching the given problem. And let's just read it, no? So this one is more like an application, no, to the given theories that we just learned. So, okay. The Hubble Space Telescope was deployed on April 24, 1990. So by the Space Shuttle Discovery. So a model of the velocity of the shuttle during the mission from the liftoff at t is equals to 0 until the solid rocket booster were jettisoned at the given time, which is 126 seconds. So we have a given equation, which is an equation of velocity given with, yeah, it's a long equation, so I will just not but you can see, no, so that is in feet per second, of course, so it is an English unit. So what is being asked, so using the given equation, so using this model, so we estimate the value of the absolute maximum and the minimum values of the acceleration. of the shuttle between the liftoff and the jettisoning of the boosters. So, yeah, as what we should understand, the maximum and the minimum values of the given application is very much critical. No? If we reach these values, then your um uh shuttle or yeah shuttle no ang kuan ki observe sa telescope will be at a critical um situation, no? So you just need to avoid this critical or absolute maximum minimum to avoid accidents. So murag as just what I understand with the problem. But we have a given equation here and we have a given time. So we have a given interval. So again, I would just be directly writing the equation. So your velocity equation is at 0.001302 t cubed and 0.09029 t squared plus 23.61 t minus 3.083. We have an interval of greater than or equal to 0 and lesser or equal to 126 seconds. So this is at seconds. Your velocity is at feet per second. So again, as what we learned, finding the critical number first and plug in those values. And since we have the values of your interval, we still need to plug in the values of interval to your function and compare, no, to get the value of the absolute maximum and the minimum. So yeah. So derive the equation first. So that is that is 2 times 0.001302 t minus this is cube pala. So this is 3 times. So this is t squared times 2 times 0.09029 t plus 23.61 and this becomes 0. So equating this to 0, I will just go directly, no? So you know already how to solve this one. By algebra, we could get the values of t. We have two values, no, because it is a quadratic equation. And also deriving this one to mention, we know that by application, this is the acceleration. And yeah, your t here, you could have what? Sorry. So you need to find the acceleration there. Let's just go back to the problem, no? So using this model to estimate the absolute maximum and minimum values of the acceleration. So you need the acceleration first, the equation of the acceleration, then derive this again to find the value of your uh, maximum and the minimum value. So we need to derive again this one because that's the thing that we're being asked by the problem, no? So the a prime of t, this is equivalent to 6 times 0.001302 t minus 2 times 0.09029. Then this becomes 0. So this one will be equate to 0. So you have linear equation. So you have value of one critical number. So this is, yeah. So this is 2 times 0.09029 divided by 6 times 0.001302. So this is equal to around 23 point, yeah, value, approximating value of the 23.12, no? So you have one value of t, so tulo lang yung i-distribute. So at time is equal to 23.12. So your a of 23.112, it is equals to 21.52. So you have two intervals, so that is at 0 and at 126. So at 0, this is equivalent to 23.61. And at 126, this is approximate to 62.87. 62.87. So by observing these three values, your absolute minimum is at 0, no? I don't know. At the t, at the time or the critical time that we get, which is equivalent to 23.12 seconds, and the absolute maximum would be the maximum, the greater time, which is the 126, no? So by conclusion, yep, the maximum acceleration that we could get would be around 62.87 at the time of 126, no, seconds. So the absolute acceleration of the given problem is at 62.87 feet per second squared, and the absolute maximum acceleration, then absolute minimum acceleration would be around 21.52 feet per second squared. No? So that's it by application. So I hope you learned something again with this video. And I hope you practice some of the problems, with maxima and minima. So by next video, we will be proceeding with the mean value theorem, and let's just go around with limits at infinity, so on and so forth. So see you again with the next video.